Entropy regularization has been widely adopted in deep reinforcement learning algorithms to enhance policy optimization performance and stability. Maximum entropy reinforcement learning, or MaxEnt RL, is a notable form of entropy regularization that simultaneously optimizes the expected return and entropy by augmenting the objective with an entropy term. Despite its theoretical and empirical successes, the practical application of MaxEnt RL in on-policy actor-critic settings remains underexplored, likely due to the difficulty of managing the entropy reward. Entropy regularization is a crucial component of many practical deep RL algorithms, such as Trust Region Policy Optimisation, which penalizes policy improvements using Kullback-Leibler divergence to regularize deviations between consecutive policies. MaxEnt RL, on the other hand, regularizes policy evaluation by augmenting the conventional RL task objective with an entropy term, promoting policies towards areas of higher expected trajectory entropy. This approach has been shown to improve exploration and robustness by promoting stochasticity. Recent theoretical advancements have provided a unified view of these approaches, suggesting that their combination could lead to faster convergence to the solution of the regularized objective. Policy gradient methods have also shown the effectiveness of MaxEnt RL in accelerating convergence. However, the practical application of MaxEnt RL, particularly in stochastic policy gradient methods in on-policy settings, remains underexplored. The authors hypothesize that this research gap is attributed to the difficulty of handling the entropy reward in practice. To address this challenge, the authors propose a simple method of separating the entropy objective from the MaxEnt RL objective, facilitating the implementation of MaxEnt RL in on-policy settings. The proposed method is evaluated empirically, demonstrating that extending Proximal Policy Optimisation and Trust Region Policy Optimisation within the MaxEnt framework improves policy optimization performance in both MuJoCo and Procgen tasks. Additionally, the results highlight MaxEnt RL's capacity to enhance generalization. These findings suggest that MaxEnt RL can be effectively applied in on-policy actor-critic settings, addressing the research gap in this area. Maximum entropy on policy actor-critic via entropy advantage estimation introduces entropy advantage policy optimization, EAPO, a method that separates task and entropy objectives of the regularized objective, addressing the issue of entropy rewards dominating task rewards and leading to overly optimistic or pessimistic policies. In standard maximum entropy (MaxEnt) policy, the return correlates with episode length, causing issues in policy evaluation. Naive MaxEnt agents fail to learn optimal stochastic policies, resulting in deterministic or wandering behavior. EAPO controls the effective horizon of entropy return estimation and entropy regularization on policy evaluation by employing a dedicated discount factor for the entropy reward and utilizing generalized advantage estimation (GAI) on each objective separately. This approach requires only minor modifications to existing advantage actor-critic algorithms, extending PPO and TRPO. EAPO's efficacy is empirically demonstrated within deterministic environments with discrete action spaces, aligning with existing theories on MaxEnt formulation and softmax policy gradient methods. The method is evaluated on discretized MuJoCo continuous control tasks, including those with infinite horizons, and tested for robustness in Procgen episodic environments. Additionally, the usefulness of MaxEnt policies is examined in the mini-grid door key environment. The considered finite discounted deterministic Markov decision process, MDP, is defined, comprising the set of states, actions, initial state distribution, transition function, reward function, and discount factors. The value function of a state under a policy is defined, which will be used in subsequent sections. Maximum entropy reinforcement learning, or MaxEnt RL, optimizes the expectation of the sum of the value and trajectory entropy with respect to the initial state distribution. This approach introduces the soft advantage function, A-pi, which combines the action value function Q-pi and the entropy advantage function A-pi-h. The soft advantage function provides a comprehensive measure, balancing between maximizing cumulative rewards and increasing policy entropy. The soft policy gradient theorem enables direct optimization of the MaxEnt RL objective by computing the gradient of the objective with respect to the policy parameters. This allows for the learning of policies that achieve a balance between exploration and exploitation in reinforcement learning tasks. By using direct policy gradient from samples, MaxEnt RL facilitates the optimization of the objective, leading to improved performance in complex environments. The soft advantage function, API, is a key component of MaxEnt RL, as it incorporates both the expected return and the entropy of the policy. This enables the agent to explore the environment while simultaneously exploiting the learned knowledge to maximize cumulative rewards. The soft policy gradient theorem provides a theoretically grounded approach for optimizing the MaxEnt RL objective, ensuring that the learned policy adapts to the environment's dynamics. Entropy Advantage Policy Optimisation, or EAPO, is a novel approach to policy optimization in reinforcement learning. By combining the value advantage function and entropy advantage function, EAPO derives the soft advantage function, which is used for policy updates. Unlike traditional methods that employ an entropy cost term to encourage exploration, EAPO leverages the maximum entropy reinforcement learning framework to direct policies towards regions of higher expected trajectory entropy. The approach is based on the approximate policy gradient theorem, which involves estimating the entropy advantage function using a separate prediction head within the conventional value critic. This allows for the estimation of the trajectory entropy of a state, essential for entropy advantage estimation. By substituting the conventional advantage estimate with the soft advantage estimate and omitting the entropy bonus term, EAPO extends popular policy gradient methods such as PPO and TRPO. In contrast to other approaches that apply both KL regularization and entropy regularization, EAPO focuses on the positive effects of using the MaxEnt framework instead of the entropy cost. Experimental results show that using the MaxEnt framework consistently improves the performance of on-policy algorithms, compared to the entropy cost method. This work contributes to the ongoing research on the theoretical properties of policy gradient methods, particularly in the context of regularized MDPs. It highlights the potential benefits of integrating the MaxEnt RL framework into on-policy algorithms, providing a new perspective on how to incorporate entropy regularization in reinforcement learning. The paper introduces maximum entropy on-policy Actor-Critic, a novel approach that integrates the benefits of both on-policy and off-policy learning. This is achieved through entropy advantage estimation, which utilizes generalized advantage estimation, GAI, to approximate the trajectory entropy V-pi-h. The entropy critic network, parameterized by omega, is trained by minimizing the mean squared error LH, omega. The entropy advantage policy optimization combines the entropy advantage with the standard advantage estimate, resulting in a soft advantage function API. This function is then incorporated into the policy objectives of PPO and TRPO, leading to modified objective functions for both algorithms. The value critic loss LV, phi, is defined as the mean square error between the estimated return value and the critic's prediction. In TRPO, the optimization problem involves maximizing the expected entropy advantage while maintaining a constraint on the KL divergence between the old and new policies. This approach allows for efficient exploration-exploitation trade-offs, enhancing the performance of on-policy reinforcement learning algorithms. The authors evaluate the performance of their proposed maximum entropy on-policy Actor-Critic algorithm, EAPO, by comparing it to baseline algorithms PPO and TRPO across various environments. These include Procgen benchmark environments, discretized continuous control tasks, and a hard exploration task. In the Procgen benchmark environments, which consist of 16 tasks with different levels of correlation between episode length and return, EAPO outperforms the baseline PPO agent in most environments. This demonstrates its efficiency in policy optimization. Moreover, it shows improved generalization capability when using higher temperature tau, which favors high entropy trajectories. For the discretized continuous controlled tasks, EPO is compared against its corresponding baselines in 4 MuJoCo environments. The results indicate that by adjusting gamma h and lambda h, EAPO can outperform or match the conventional entropy regularization method throughout all environments. However, the performance gain is relatively modest, suggesting that EAPO may be less efficient for continuing tasks. The authors also investigate the impact of the Guy lambda H hyperparameter for the entropy advantage estimation, finding that it does not significantly affect the performance. This suggests that adjusting gamma H and tau would be sufficient for most cases. Overall, the experiments demonstrate the potential of EAPO in improving policy optimization and generalization capabilities in various environments. The results provide insights into the hyperparameter tuning and the efficacy of separating the MaxEnt objective from the reward function. The Entropy Advantage Policy Optimisation (EAPO) algorithm is evaluated in various Procgen benchmark environments, where its performance is compared to PPO agents in 16 different environments. Figure 2's left panel displays the generalization test results of EAPO agents with two temperatures, tau equals 0.02 and tau equals 0.005, against PPO agents with entropy coefficients of 0.001 and 0.01. The results show that EAPO consistently outperforms or matches PPO in all environments, with the mean episodic return shown for each environment and a 95% confidence interval indicated by the shaded area. The right panel of Figure 2 presents the mean normalized score for both test and training environments, computed according to Cobb et al., 2020. Table 1 provides the mean episodic return at the final time step of tests on 100 unseen levels for each environment, along with the 95% confidence interval from 10 different seeds. The results indicate that EAPO agents achieve higher mean episodic returns than PPO agents in most environments, with some exceptions where the performance is similar. The normalized scores also demonstrate that EAPO outperforms PPO in terms of generalization capabilities. The authors report the mean and 95% confidence interval for each environment, providing a comprehensive overview of the performance of EAPO and PPO agents. These results suggest that EAPO is a promising approach for on-policy actor-critic methods, achieving better generalization capabilities than PPO in various Procgen environments. The Entropy Advantage Policy Optimisation (EAPO) algorithm is a novel, model-free, on-policy actor-critic method that builds upon the maximum entropy reinforcement learning framework. This framework aims to enhance generalization and exploration in reinforcement learning tasks. EAPO can be seamlessly adapted to various advantage actor-critic algorithms, such as PPO and TRPO. Empirical evaluations demonstrate improved performance compared to conventional entropy regularization methods. EAPO is evaluated in several environments from the Procgen benchmark suite, including Dodgeball, Chaser, Leaper, and Bossfight. The mean episodic trajectory entropy and return of EAPO are compared to PPO-based algorithms using different entropy coefficients. Results show that EAPO achieves higher trajectory entropy and better generalization performance than PPO, particularly in environments requiring exploration and adaptation. Furthermore, EAPO is tested in the mini-grid Door-Key 8x8 environment, a hard exploration task. While EAPO solves this task within 5 million frames for all 10 seeds, the baseline PPO only achieves the goal for 3 seeds. However, the authors note that this task is highly sensitive to hyperparameters, and entropy regularization may not effectively mitigate epistemic uncertainty. The simplicity of on-policy algorithms in EAPO is expected to encourage broader applications of the MaxEnt RL algorithm to promising areas like competitive reinforcement learning and robust reinforcement learning. Overall, EAPO has the potential to replace conventional entropy regularization methods and enhance generalization in reinforcement learning tasks. This section of the research paper presents a comparative analysis of the performance of the proposed maximum entropy on policy actor-critic via entropy advantage estimation (EAPO) algorithm against other state-of-the-art reinforcement learning algorithms, specifically PPO and TRPO, in various MuJoCo tasks. The comparison is based on mean episodic return and trajectory entropy. The results are displayed in Figure 4. Where EAPO is compared to PPO and TRPO with their best-performing entropy coefficients, as well as versions augmented with an entropy reward. The top panel shows that EAPO-PPO outperforms both the standard PPO and the entropy reward augmented PPO in terms of mean episodic return across all 4 tasks. AntiV4, Walker 2 DV4, half-cheetah v4, and humanoid 4. The bottom panel demonstrates a similar trend for EAPO-TRPO, with EAPO surpassing both the standard TRPO and its entropy reward augmented counterpart. Additionally, Figure 5 presents a comparison between EAPO and PPO in terms of both mean episodic return and trajectory entropy on the mini-grid Door-Key 8x8v0 environment. The EAPO algorithm with parameters tau equals 1e5, gamma h equals 0.8, and lambda h equals 0 shows superior performance in both metrics when compared to PPO with entropy coefficients of 0.01 and 0.001. The shaded areas in the figures represent the 95% confidence intervals, indicating the variability in performance across different random seeds. Overall, this section highlights the efficacy of the EAPO algorithm in enhancing the exploration-exploitation trade-off in reinforcement learning tasks, leading to improved performance and higher entropy trajectories compared to existing methods. Maximum Entropy on Policy Actor-Critic, or MEOPAC, is a novel algorithm that leverages entropy advantage estimation to enhance policy optimization in reinforcement learning. By combining the benefits of value-based and policy-based methods, MEOPAC enables efficient exploration and exploitation in complex environments. Building upon the theory of policy gradient methods, MEOPAC addresses issues related to policy optimization with entropy regularization. The algorithm utilizes a novel entropy advantage estimator, derived from entropy-regularized Markov decision processes, which introduces an additional term in the objective function that encourages exploration. This estimator is inspired by the work of Choe et al. 2017, and is shown to improve the efficiency of policy updates. MEOPAC is connected to other reinforcement learning frameworks, such as Soft Actor-Critic and Trust Region Policy Optimisation, and can be viewed as a special case of these algorithms when considering specific choices for the entropy coefficient and the trust region constraint. Theoretical analysis demonstrates that MEOPAC achieves linear convergence rates, similar to those obtained in softmax policy gradient methods. The algorithm is evaluated in various environments, including grid-world and mini-world tasks, showcasing its effectiveness in solving goal-oriented problems efficiently. Practical insights into the implementation of MEOPAC are also provided, including discussions on hyperparameter tuning and the use of asynchronous methods for parallelizing the computation of entropy advantage estimates, inspired by MNIH et al. 2016. Maximum Entropy on Policy Actor-Critic, MEOPAC, is an on-policy actor-critic algorithm that leverages entropy advantage estimation to enhance exploration and improve policy optimization in reinforcement learning. Building upon Proximal Policy Optimisation (PPO) algorithms, MEOPAC incorporates the principle of maximum causal entropy to encourage exploration in the policy optimization process. By adding an entropy term to the objective function, the algorithm maximizes both the cumulative reward and the entropy of the policy, striking a balance between exploitation and exploration. The entropy advantage, a measure of how much better a particular action is compared to the average action under the current policy, is crucial for guiding policy updates and avoiding local optima. The authors demonstrate an efficient and computationally cheap method for estimating the entropy advantage, making it practical for real-world applications. Compared to state-of-the-art algorithms such as Soft Policy Gradient Method, SPGM, and Mirror Descent Policy Optimisation, MDPO, MEOPAC exhibits superior performance and computational efficiency. The authors also emphasize the importance of carefully tuning hyperparameters, particularly the entropy coefficient, which significantly influences the exploration-exploitation trade-off and overall algorithm performance. Empirical evaluations on MuJoCo benchmark environments, including Hopper, Walker 2D, and half-cheetah, demonstrate that MEOPAC outperforms existing methods, especially in high-dimensional action spaces and sparse rewards. The paper concludes by highlighting the potential of MEOPAC for solving complex reinforcement learning problems and providing an open-source implementation for researchers to apply the algorithm in their own experiments. The soft policy gradient theorem is a crucial component in understanding maximum entropy on policy actor-critic methods via entropy advantage estimation. This theorem revolves around the discounted state distributions induced by a policy pi, denoted as RP(S) and RP(H's), for discount factors gamma v and gamma h, respectively. The proof consists of two primary components: the first term, representing the expectation over state and action distributions, and the second term, accounting for entropy advantage estimation. To demonstrate the efficacy of the proposed approach, experiments were conducted on various tasks, including the mini-grid empty 8x8v0 environment. In this example, the action space comprises 7 discrete actions, with a reward provided only when the agent reaches the goal state. The observation utilized is the full 8x8x3 image without partial observability, and a simple convolutional neural network (CNN) architecture serves as a shared feature extractor. The network architecture for discretized and continuous MuJoCo tasks, as well as the Procgen benchmark experiments, is also discussed. The MuJoCo tasks employ a combination of fully connected and convolutional layers, while the Procgen benchmark utilizes a more complex architecture incorporating attention mechanisms and recurrent layers. Hyperparameters for these setups are provided, including learning rates, batch sizes, and entropy coefficients. Additional experiments were conducted to validate the proposed approach. These experiments involve varying the discount factors, entropy coefficients, and learning rates to assess the robustness of the method. The results demonstrate the effectiveness of the proposed approach in solving complex tasks and highlight the importance of entropy advantage estimation in on-policy actor-critic methods. The research paper presents two tables detailing the hyperparameters used in experiments across various environments, including MuJoCo, Procgen, empty, Dorkey, and others. Table 2 outlines common hyperparameters such as the number of time steps, environments, steps, learning rate, batch size, epochs, discount factor, Guy lambda, clip range epsilon, max gradient norm, and other hyperparameters. These hyperparameters are tailored to each environment, with some shared across multiple environments. For instance, the learning rate is set to 5 times 10⁻⁻⁴ for MuJoCo, PPO, and MuJoCo, TRPO, while it is set to 1 times 10⁻⁻³ for Procgen empty and Dorkey. The batch size is set to 1024 for most environments, except for Procgen, where it is set to 2048. Table 3 focuses on the EPO-specific hyperparameters, including gamma h, lambda h, tau, and C2. These hyperparameters are also environment-dependent, with different values assigned to each environment. For example, gamma h is set to 0.8, 0.9 for Procgen empty and Dorkey, while it is set to 0.8 for MuJoCo, PPO, and 0.9 for MuJoCo, TRPO. The hyperparameters in both tables play a crucial role in tuning the performance of the maximum entropy on-policy actor-critic algorithm via entropy advantage estimation. The specific choices of these hyperparameters can significantly impact the learning process and the ultimate performance of the algorithm in various environments. The performance comparison of the proposed maximum entropy on-policy actor-critic algorithm, denoted as EAPO, with several variants of Proximal Policy Optimisation, PPO, on 4 different MuJoCo continuous locomotion tasks is presented. These tasks include anti-V4, Walker 2D V4, half-cheetah V4, and hopper 4. Each task is evaluated based on its mean episodic return over a specified number of time steps. The plots illustrate that EAPO consistently outperforms PPO in terms of achieving higher mean episodic returns across all tasks, especially at the beginning stages. This suggests that EAPO's ability to estimate entropy advantage effectively contributes to its superior performance. The PPO variants are differentiated by their entropy reward coefficients, which are set to 0.05, and different clipping parameters, C, of 0.0001, 0.001, and 0.01. The results indicate that varying these parameters does not significantly impact the performance of PPO, as it consistently underperforms compared to EAPO. The plots also demonstrate that EAPO's performance improves as the number of time steps increases, indicating its potential for long-term learning. In contrast, PPO's performance tends to plateau or even decrease with more time steps, suggesting limitations in its ability to adapt and learn over time. In conclusion, this page provides empirical evidence supporting the effectiveness of the proposed EAPO algorithm in continuous locomotion tasks, highlighting its potential for enhancing reinforcement learning capabilities in complex environments. Reinforcement learning algorithms are evaluated in various environments and under different hyperparameters in a comparative analysis. The Entropy Advantage Policy Optimisation (EAPO) algorithm is the primary focus, utilizing maximum entropy on policy actor-critic methods to estimate the entropy advantage. By incorporating an entropy term into the policy optimization objective, EAPO aims to improve the exploration-exploitation trade-off. 4 standard continuous controlled tasks AntiV4, Walker-2 DV4, Half-Cheetah V4, and Humanoid 4 are used to evaluate EAPO's performance in the gym environment. These tasks represent a diverse range of challenges in terms of complexity and dimensionality. The results show that EAPO outperforms state-of-the-art algorithms, such as PPO, TRPO, and DDPG, in most environments, suggesting that incorporating the entropy advantage estimation can significantly enhance policy optimization efficiency. To understand the impact of specific hyperparameters on EAPO's performance, an ablation study is conducted. The effects of varying the entropy coefficient, gamma h, advantage coefficient, lambda h, and temperature, tau, on the mean episodic return are investigated. The findings indicate that the choice of these hyperparameters significantly influences the algorithm's performance, with optimal settings varying across different environments. The research demonstrates the potential of EAPO in improving reinforcement learning outcomes by leveraging maximum entropy on policy actor-critic methods. It also highlights the importance of carefully tuning hyperparameters to achieve optimal results.